welcome back to another episode of the series Building an Autonomous Robot from Scratch. Now, in today's episode, we will be developing our driver or a wrapper in ROS to communicate with our Arduino board, essentially, that will control the motors, right? And yeah, um, so before we start, let me share here my screen. I will be developing this on my PC, and I advise you to do the same. And either way, you will need to install ROS in your PC if you haven't yet do it, um, because you will need any other PC really to then control your robots with Wi-Fi, or yeah, essentially with Wi-Fi. And so yeah, I advise you to install the ROS Iron Desktop instead of the base that we installed on the Raspberry Pi of in the previous episode. So you just need to follow the tutorial here in ROS. Okay. Now, so I have already created I have already developed this driver, and it is working. So you can find it on the Perceptron bots repo as well. So this is the Perceptron workspace, which is essentially what we will be creating. And so yeah, this is the driver. So we will have here the driver, and yes, so we will be developing this one right here to get our robot moving, right? So let's just get started, shall we? So the first step we should do in this case is to create a workspace. Now, a workspace is needed for in our case because we will have multiple ROS nodes in the future. And so I like to subdivide the workspace into categories. So in this case, we will be developing the driver. And so we have a drivers folder, right? We will have some generic folder which will contain bring up. So bring ups is essentially launch files that allow us to easily launch multiple nodes at the same time. Then we might have navigation, right? For example, SLAM or planners and so on, and maybe some third parties. For the drivers, I think we will have two, right? So we have this one that we will be developing, and you will have one for your lidar, right? But that will be in the future. So what we'll do, let's create a Perceptron workspace, and in this we will create a source folder, and we specify the tag P to create multiple folders at the same time. And there we go. So now go ahead and go to your Perceptron workspace in the source, and actually we'll need to create another folder, drivers, right? And let's go again to drivers. Now we are inside this driver folder, and we need to create our ROS2 package. So to create one, first of all, make sure you source the ROS. So usually you do source /opt ROS iron setup.bash, or in my case I do zsh because I have a zsh shell. So it will depend on which shell you are using. If you are using the default, then it's the bash, okay? So once you do that, now we can do ROS2 package create a build type amend Python, because we will be creating a Python package, and then the name of the package, which I call here Perceptron driver. Okay, so this will create us a package Perceptron driver. So go ahead and go inside, and here now we have a few things. So we have a package.xml, we have a setup.config, setup.py, test folder, resource folder, and Perceptron driver folder. So the package.xml essentially gives you the structure of your package, such as like dependencies dependencies it needs, and so on. And then you have the setup.py, which is basically a Python, yeah, just specify like you have a package, a Python package, sorry. The test one we don't really need, so I will just remove test like this. So now let's go into the package.xml, and here you can see that there is some to-dos. So we can, you know, add some description like a driver to communicate with Arduino, something like this. License, we don't really have one for now. I mean, you don't need to create one, and so this we can leave as is. Now we have the setup.py, and then here we can do the same. For example, description, and we can, you know, so for example, we can copy this and we can paste it here like so. So yeah, we will come back at this file here eventually, because we will need to have here which script we'll need to launch. Okay. Cool. And that's basically it for now, what we need to do. We don't really need to, I mean, we are not obliged to change these, right? We don't need to change any of these description, license and so on. That can be, that's up to you really. Okay. So now we need to create two files essentially. So we will create a, node, which is the one that we will run, and we will create a serializers.py file as well. And I will explain this in a bit. So we are in the root folder, and now we need to create two files inside the Perceptron driver folder. So let's touch Perceptron driver, and then let's create driver node.py, and also Perceptron driver serializers, or serializer, yeah, .py. Okay, like this. Cool. So if we go and do ls Perceptron driver, we have the two files. Okay, plus this init file, which is it's a Python generated code. Okay. All right. So let's go to our nodes. Okay, driver node. And we will need to import some stuff. So we will need to import, first of all, the RCLPy, which is the ROS library for Python. We will need to import time. So I'm just copying here what I have. Serial, which will be used to communicate with the serial devices, such as the Arduino, sorry. Then we need from RCLPy .nodes, import nodes. We will need from geometry messages.message, import twist. So the twist message is essentially what we will be using to receive velocity commands and then send to the driver, right? So to the Arduino. We'll need from nav messages.message, import odometry. So the odometry will be essentially what we will publish from the robot, right? Because we are computing, if you remember, the position of the robot, right? Which is essentially the odometry. And then we will need two things from the, so we will need from a Perceptron driver.serializers, import serialize, let's see, serialize odom message and create TF transform. So these two functions are still not created. This will come later, okay? And later on we'll need import TF2 ROS. Okay, cool. So these are all the different, Python libraries we'll need. And now we can start creating the actual node. Let me disable Copilot actually. All right, so we start by creating a class. Let's call it driver node, and we inherit the node class from ROS. And let's create the construction, which is init, like so. And no, we don't need all of this. So nor all of this. So, oops, sorry. Okay, so we create the driver node where we pass the node name, which we will define later on, and this will send to the node class here the node name. Okay, so we will need some variables, some attributes for the class, and I like to define these on top of it, on top of the init constructor, because I don't know, it just seems easier to read. So basically now we need to create, so I mean, you don't necessarily need to create these, but they are useful because you can later on change it easily. What I mean by this is we will have topic names, frame names, and whatnot. And we could easily hardcode those, but I believe it's better to not hardcode those and store them as variables. And then we can use the parameter server to basically change all these parameters very easily with a config file, pretty much. Okay, so you will see this will become very handy later on. So let's start by creating these variables, these attributes. So command velocity topic name, okay, and now we'll be using here the default one, so we don't really need but this slash, but I will either way add it, I guess. cmd vel. This is the standard name, I guess. Then we have odom topic name. So this is where we will publish the odometry. We will need base link frame ID, and I will call this base link. So all these names are standard names, okay? Odom frame ID, and I will call this odom, okay? So essentially these are all the topics we will need for this node. So again, we have this command velocity topic, which will be used to receive velocity commands. Odom topic will be used to publish odometry. And then we have these two frame IDs, and this will be used for a TF transform. So we will have a TF transform from the odometry to the base link, which is, base link is the robot itself, okay? And so essentially the odometry will be relative to this odom frame and the base link frame, right? So essentially odom is always 0, is the point 0, 0 in the map, and the base link is where the robot is within the map, okay? And now you can call these whatever you want, okay? You can call this robots, so whatever, doesn't really matter, okay? But usually this is the names you give, so I am using the default ones. Then we will need subscribers and publishers. So let's create a command val sub, right, which will subscribe. For now it's none. cmd, not cmd, odom pub, which is also none. So we are just declaring these things. We need a odom timer frequency, which will be 10 as in hertz, okay? We will be publishing the odometry 10 times a second. We will need a TF broadcast timer, and also none. And then some configuration. So we will need to know what is the serial port we should communicate with. By default, I will say this dev /tty USB 0. And then we need the baud rate as well, serial baud rate, which is equal to 9600, which is the one by default used in the Arduino, right? If you have changed this value in your Arduino code, then you will also need to change this value here, okay? Not that you need to change, so you don't need to change any of these values to yours, and you will see why in a bit. Because we will be using this parameters server to easily change these values, essentially. We will need also a flag, so reset flag or oddom flag. And this will be set to true by default. And what we will do is essentially every time you launch this node, the odometry on the Arduino will be resetted. And the reason this works is because I have implemented this in the Arduino controller, okay? So make sure if you are using the motor controller driver to use the latest version on GitHub. Okay, so these are all the attributes we'll need. And now essentially we can proceed to writing the code, okay? So let me check here what I have. So essentially the first part will be to read the parameters, okay? For this I will define a function, read params, and this will pass the self. And so read params will essentially get the values that are in the parameter server of ROS. If none of the parameters we are searching for are, if they are not available, we will use then these values as the default values, okay? So now the way we do this, so this will be a big file or a big function essentially. So I will copy what I have here and I will explain you what I did, okay? Okay. So as you can see, this is quite a big file or quite a big function, but there's nothing much going on essentially. So the first thing we need to do is to actually declare a parameter. So here we are doing, well, we want to declare the parameter by the name serial port, and we are giving a default value of self serial port. Okay, in case this parameter does not exist, we are actually creating one and passing this default value, which is the ones we define here on top. Okay, so we do this for all the parameters that we want. So the port, the baud rate, the velocity topic name, the baselink frame ID, oddom frame ID, and a reset odometry flag. Then we get the value by saying self.getParameter, and then we pass the name, and then we call the function getParameterValue, and we convert this to a string value, okay? Because this is a string. For example, in the baud rate, you need the integer value, so we convert this to an integer value, okay? And you do the rest for the other ones. And for the flag, we convert it to Boolean variable, value, sorry. So this is it for the read params. And so now here we do self.read params. And what will this will ensure then that whatever we call after this, we will have the updated params if we have updated them, okay? So then we need to start the connection between the Raspberry Pi, a computer, whatever, with the Arduino, okay? So we basically now go and do a try block, and this is just in case something bad happens. And so we do serial serial. Then here we specify the port, so self dot serial ports, right? Just be sure, yeah. Self.serial baud rate. And we also set a timeout of 0.5. So this timeout will basically make this, in case we send a command, it will only wait for 0.5 seconds. And in case it doesn't receive anything back, it just proceeds. So it doesn't stop. And so we start this as self.serial. Okay. So that's it, and then we accept the error, so serial.serial exception, and then we print something. So self.getLogger dot error, and then we say could not open serial port. Serial port. Okay. Cool. So now, if all goes well and we have something connected, this will not fail. And after this, we will still give it a check. So we do a time.sleep to give a bit of time, so of 2 seconds. And then we would do, or create a function, define check serial, I believe. Yeah, check serial. That will take the self as parameter. And this will check if self.serial.is open. If that is the case, if it's not, then again we do a self.error. So let's copy this. What am I doing here? Copy this, and we do exit even. So we get serial port is not open. Could not, I don't know, could not communicate with port self.serial port, and then we exit the program. Now we do self.check serial, and if the port is open, then it's all fine. Okay. Cool. Now we need to check if the self reset DOM flag is enabled. We will need to do something here. Okay, so reset. If not, we don't do anything. And afterwards, we need self.init subs, self.init pubs, and self.init timers. So I like to do this way, because then otherwise you would need, like, you would basically be populating this init method with a lot of things, and this way we can split up things. Okay. So let's create this self init. This init subs, init pubs, and init timers. So define init subs. Again, this will take self pass. So we create the timers pubs. Okay. So subs, we only have one essentially. So self.cmd val sub equals a self.create subscription. Now this takes the message type, and the message type is the twist. This takes the topic, which is self.velocity command cmd velocity topic name, like this. And then it also takes a callback. which we will say it's the self.cmd val callback, which we didn't create yet, and that's it. And then we pass a 1. So this one is the queue, and we only consider one message. So that's it for the subs. It might be useless to have this. I mean, these 3 methods here just for one thing, but it's nice to do it for the future. So now we have pub. So self.odompub equals self.create publisher. And again, this takes the message type, which is odometry, and the topic name, which is self.odom odom topic name. And yeah, we say it's with a 1 as well, if I'm not wrong. Yes. Okay. And I think that's all for the pubs. Oh, never mind. So we have a self.tf broadcaster, tf broadcaster equals tf2 tf2 ROS dot create not create but transform broadcaster, and then the self. Yep. Wait, I think I said here tf broadcaster timer, but I'm not sure I need this. It's this tf broadcaster. Okay, so now timers. We will need self.odom timer. I did not add this timer, did I? I did not. Yeah, so it's self.odom. Let me see the name I have. So odom pub timer equals self.create timer, and then we need a period. So we have the frequency, so 1 divided by self odom timer frequency, like so. And the callback, so we need a callback function, so self.odom callback. All right, so let me just create this one here, just to be consistent. Cool, so now we have all these, right? And now we are missing this reset. So let's create def reset odom self. We will pass. We'll need a define odom callback self, and then the message as well. And def, actually no, this is odometry, so we will not have any message, but we will need for the cmd val callback self and the message. Pass. So this is a twist message, so that we will know what type this message is, and that's it. Okay. So let me check here. First of all, the reset odom. Okay. So now here we will need to send something via serial to the Arduino so that it resets on the Arduino. Okay. So the command will be equal to reset \n. Okay. And then we say self.serial dot right, and then we say cmd.encode like this. I am not wrong. Let me check. So self.0, yep. Yep. So now we sent, and now we check. Did we receive something? So self.serial dot read line and dot decode dot rstrip. Okay. Yep. Ah, yep. Okay, so now we say if ACK is infinite or equal, then OK \n. We say something went wrong, so self dot get logger dot error error resetting odometry. Okay, we are good with this. So now to the init method. Here we say self.reset odom. Good. So we have two methods missing now. And so let's now do the command velocity. Okay. So we need the command. So cmd again. And this command will be starting with a C, if I'm not wrong. Yes. Or I guess this is the flag. So now remember that the way we are checking in the Arduino is we have a flag. So we have a flag, some value X and some value W for the velocity command, right? And the flag for this is C. Then we say X equals message dot linear dot X, and we need to multiply this by 1000, if I'm not wrong. Yes, times 1000, and then do the same for message dot linear, not linear but angular dot Z times 1000. And we need to convert this to an integer just in case. Okay. All right. So now the final command cmd equals. So we create a f string. So we pass the flag, a space x, a space w, with the curly braces, of course. Okay. Now we do the same. So self.serial.write, we do cmd.encode, and then if, or ack, or I guess we can do this. Error sending velocity command. All right. Cool. Now, odometry callback. So this one is a bit more challenging. So we will need this flag still. And then instead of C, it's the O, right? Actually, no, it's the Q. Okay, it's the Q. And this flag, it's like, oh, maybe I forgot something here. Of course. We're missing the \n for the velocity command. Yep. Okay, so we have the Q, and now we say self.serial.write. Well, in this case, this is the command. So cmd dot encode. Now we will get back the pose. So pose equals, we need to first, oh, never mind, self.serial.readLine. So now we do .decode. .rstrip, or I don't have that, but it doesn't hurt having that. So we'll create a now, which is the current time we are receiving this. So it's self.getClock .now, and we will need a try block again. Pose equals floats q for q in pose.split by space. Okay. Remember that the way we are sending back the odometry is we do x, y, z, all splitted by a space. Okay. And that is important because now, again, we split the string by the spaces and we'll have x, y, z as a list. If something goes wrong here, it could be that what we are receiving is not as we intend to do, so it might not be x space b y space z, but it could be something else. And so we need to have this failure. In case this fails, we need to have some exception. Self.getLogger.error error reading odometry. Okay. And now we do odom message equals serialize odom message. And so we will need to create this. Okay. Then we do tf odom base equals, so from odom to base, create tf transform, which we also don't have. And then we say self.odom pub.publish odom message and self.tf broadcaster.send transform tf odom to base. Before we go to this serializer, let's create another function of method. Define close serial. This will be needed after serial. This does self.serial.close, like so. Okay, so let's now create this, or to write these functions in the serializer. All right, so from here we will also need this here, and we will need rclpi.time import time, and from tf to ROS dot import transform stamped, and from tf transformations import quaternion from Euler. So this TF transformations you will not have, as I don't have either. This is because this does not come with ROS by default. And with this, we need to install them manually. To do this, we will need to install two things. So the first thing is sudo apt install ROS iron tf transformations. Okay, this is one, and then pip sudo pip3 install transform transform 3D. So with these two, we should now be able to get LSP restart. All right, so now we are good. And so we need two functions. So define serialize Adam message. Now this needs a frame ID, which is a string. This needs a child frame ID, which is a string. We need the time, which is the time. We need the x, which is a float. We need the y, which is also a float. And we need the theta, which is also a float. So frame ID is the essentially the Adam frame ID we have. So it's the 0, of the map. Child frame ID is the base link where the robot, so the robot essentially. So the time is the time we are creating this message, and then XYZ, which is, and theta, which is the information we have from the robot. Now, we need to create a message. So message equals odometry, and message dot linear. Pose dot linear. No, pose again. Position dot x equals x. Message dot pose dot position dot y equals y. Message dot pose dot orientation dot z equals theta. Message dot other dot frame ID equals frame ID. Message dot other dot stamp equals now. Message dot other dot not frame ID, child. No. Let me check what I have. Yeah, it's just child frame ID equals child frame ID. And yes, oh yeah, this needs to be to message, by the way. So let me just double check I am not missing anything. Okay, I am actually missing something. We need to convert, so we have basically Euler angles from Arduino, but we need quaternions instead of Euler angles. For this, we need to use this TF transformations. That's why we need this. Okay. So the first step is to create this quaternion. So Q equals quaternion from Euler, and now we need to pass the theta 0, theta. So in this case, we don't have any x or y, right? We only have rotation along the z-axis. So now we have this, and then so we need it's q dot z q or q2. So now we need to have x, y, z, and w. So it's 0, 1, 2, and then 3. Yep. And then we say return message. And in that node, we can do return a odometry message. Okay. Now we need define, create, TF transform. And now again, we need a parent, which is a string, a child, which is also a string, a now, the time, x, which is a float, y, which is a float, and theta, which is a float. So essentially the same things, and this will return us a transform stamped. So we have the TF transform stamped, TF dot stamp or other stamp equals now dot to message, TF dot parents or other dot parent, no, let's write this, other dot frame ID equals parent. Nope. What did I import here? This thing. Parents. TF.other, maybe not other, yeah, just child. Frame ID equals child. And that's that for that. So now we have tf.transform.translation.x equals x, tf.transform.translation.y equals y. And now we need to do the same as we did here. So we have q, then we have tf.transform.rotation.x equals q0. Let's copy this one more time. So y 1, 2, z, and then w 3. All right, and then we return tf. All right, so I believe we are done with this. So back to the nodes. Let's go to the odometry here. And now we need to say serialize, we need to pass in the values. So we have the frame ID, so self.odom frame ID, self.base link frame ID, and then the X, Y, or actually it's not X, Y, Z, but pose 0, pose 1, and pose 2. All right, so let's copy this and let's do it like this. All right, so I believe we are done. Let me double check. So yeah, base link, odom frame ID. I actually have something wrong. Here it's the opposite. It's the inverse. And let me check why. So parent child frame ID and child frame ID. Yeah, okay, yeah. Odom frame ID, this link. Wait, I'm not too sure. It should be like this. Maybe I have it wrong actually on mine, now that I'm thinking. Because the frame ID itself should be Odom. We can double check this actually. So odometry ROS message. We can double check this. So indeed we have other, we have the child frame ID. Estimation velocity. Poses the message should be specified coordinate frame given by other frame ID. Yeah, by the other. So actually, yeah, it needs to be Odom. No, it is correct. I mean, yeah. I think we are correct here. So never mind. I believe we are correct. If not, we can see that. Okay, so I believe this is now complete in terms of the node class. Just double checking. Yeah, I believe this is all. So the last step we need to do here is to create, well, to actually call this node when we execute this script. So we create a main function, and this main function, the first thing we'll need to do is rcl.py.init, and now we could maybe pass the args, but yeah, args equals none by default, so args. Then we need to create a node, so driver node equals driver node. And very important, we need to pass the name of the node. So let's call it Perceptron driver. Then rcl.py.spin the driver nodes. And once this has finished, we want to close the serial connection. So driver node.close serial. That's why we created this method, okay? And then rcl.py.shutdown. And that's it. Now we do if main, we call the main function, okay? Like this. Cool. Maybe we can add a print statement here, like self.getLogger .info, driver is ready. All right, so there's one more thing we need to do now, and let's go to the setup.py, and in the console scripts, all right, we need to add the following. I never know this by heart, by the way. All right, so first thing is the name we want to call this. So driver node equals Perceptron driver node, exactly, basically this, okay? So what does this mean? Well, we have the package named Perceptron driver, and we have the file named driver node, and then we are calling the main function. That's essentially what it is doing. So what we did in the driver node here, that's what it is doing, okay? It is calling this function. All right, cool. And now we can actually test this. So let's go back to the Perceptron workspace root folder, okay? Now let's do colcon build, and then we do symlink install, and fingers crossed it is working. So it has finished. Now the warnings I am getting here is due to setup.tools. I guess I should the reason is I have like a latest version of the setup.tools, but ROS, it is not supposed to work with this version. So I mean, I can actually show you. So pip install setup tools with the version, I think it's 58. Equals, yes. I think it's this. And there you go. See, no more errors. So if you have those, if you have those message warnings, you already know how to do it, okay? Now, next step, we need to source install install/setup.zsh for me. If you have the normal this default terminal, use bash, okay? I need to use zsh. There you go. Now ROS2 run Perceptron. So I don't have auto completion, so let's do this. So in case you are using zsh and you don't have auto completion, run this evaluation, and now we should have it. So you don't need this if you are using bash, most likely. So ROS2 run Perceptron, and then we complete with the tab driver node. And installing by hand required. Please run So we did install this. I don't know why. Oh, it's transforms. I had a typo. All right. So something is wrong. Init takes 0 positional arguments, but 1 was given. What did I do wrong? Oh, of course. I see. So let's go to source, drivers, Perceptron driver, and then driver nodes. Back here, it's args equals args. All right, so if you do cd minus, you go back to where you were before. So do colcon build again. And let's run this. Could not open serial port dev USB 0. And that is actually correct because I have nothing connected to it. Now, how can we test this is working? And now comes a part where I don't have the answer if you are using a Raspberry. Well, I do have the answer actually, but so I have been playing around with the Raspberry Pi on my side, and there is a problem actually. Let me change to the camera. So remember, let me check here if I have boards. All right. When assembling the robot, I told you to basically, so in the Arduino board, right? I don't know if this will focus, but so here we have 2 pins, TX and RX. And we have the same on the Raspberry Pi, TX and RX. So essentially, we just need to, so this is the Raspberry Pi, this is the Arduino. We connect the RX from the Raspberry Pi to the TX of the Arduino, and the RX from the Raspberry Pi to the TX of the Arduino. So we basically inverse both. The problem I am having is I am not able to receive anything from the Arduino in the Raspberry Pi, but I can send. And the question I don't have, or the answer I don't have is, did I fry the pin on my Raspberry Pi? And the reason I say this is I found out that the Raspberry Pi pins only take 3.3 volts, but the Raspberry Pi is outputting 5 volts. So I might have fried the pin. Now I tried playing around connecting to another RxCX pins on the Raspberry Pi, and this time sending it 3.3 volts, but it did not work for some reason as well. And so now I'm kind of stuck on this, because with the Odroid board that I'm using, everything works fine. I did not have any problems, and I can communicate with the two via cable. Now the solution I have for you, and it might be the simplest one, is the following. So if you go to Amazon, for example, let me go to my Amazon link, and if you search for UART USB adapter, so you will have these things, like this thing, for example. And so this, as you can see here, we have the TX and RX pins, and that's all you need. Okay, so and then you just connect this to your Raspberry Pi via USB, and you will see that you will have the device TTY USB 0, or it depends, something TTY USB AMC0, something like that. Okay, and that's basically what you set. If you remember, source drivers, Perceptron driver node. Here we have the TTY USB 0. This might be the one you will have, might not. So it will depend on your PC, really. Okay. So that's the solution I have for you if you are using Raspberry Pi. If you figure out how to make this connection, feel free to leave a comment. I have tried everything, so yeah, just send a comment if you know how we can solve this. But yeah, if you manage, I mean, if you don't know to solve this, just buy this USB thing, and then it should be yeah, good to go. Okay. Cool. So let's finish this driver. Okay. So now we have the driver working. I mean, supposedly it should work now. I know this worked because I have tested on mine. But we want to make this a bit easier to change in terms of parameters, okay? And how can we do this? Let's first of all create a folder inside the Perceptron driver, make the config, okay? And inside this config folder, we will create a params.yml file. And let's open this params file, okay? Now I will copy what I have here, because all right, so what do we have here? The first thing is what is the node name that we are using? In our case, the default name is Perceptron driver, and then we need this ROS parameters. Okay, we need this. It's mandatory to have, and then inside we will list all the different parameters we want to have. So we have the command velocity topic name, the ODOM frame ID, which is, I notice I have a typo here, baselink frame ID, serial port, serial baud rate, and reset ODOM. So as you can see here on the serial port, for example, I have TTY S1. And the reason why I have S1 is because on my Odroid, my port is set to S1. So that's the reason. Now, if you change basically this thing here, the topic name will change accordingly, because if you remember, we have the read params. Where is it? Read params. So we have done this here, okay? And this will ensure that once we change the parameters here, it will also change accordingly. But we will need to do something else, and that is to pass this parameter somewhere, okay? And that is what we need to do. Now, there are two ways we can do this. So the first one is ROS to run Perceptron driver, and then we need to like I don't even know, it's like ROS args, something like this. Then we need to pass here like the name of the file. It's something like this. I don't remember by heart. Another solution, and I believe we should have, is to create a launch file. So launch files usually have their own place in a launch folder, which I create here. And actually, I need to create, sorry, launch like this. And now let's create a Perceptron launch.py. All right. Let me get this file, because this essentially is always the same, okay? Okay, so let's go through this. So first of all, we import all the necessary things we need, okay? This is usually always the same for almost every launch file. And then we need to have a function generate launch description, okay? You need to have this function because this will be called when you launch a file. Then we create we need to know where this package, our package, lives, and we can get this by using get package share directory from the amend packages. And so this will get us the path to where this package lives when we build, right? And then we say what is the default parameters, and the default parameters is the one we created, okay? And this lives in the package folder under the config and the params.yaml, okay? And then we create an argument, params file, which the default value is a default param file. And we set a description, right? If up to you, doesn't really need to have one. And then we create a launch configuration with the name params file. So this is for getting the parameters file. Then we create the node itself, right? So we launch a node which has the package name as Perceptron driver. The executable is the driver node, basically as we did to launch. So ROS to run Perceptron driver node. Then we say output to be screen, and this will allow it to, when we do self .log, right? This will actually print out to the screen. Otherwise, you will only see it if you go to the ROS out topic, I believe it's called. And now we pass the parameters file to the node itself, okay? And then we say we return a launch description, which has a file argument and the driver node, okay? So this is always the same pretty much. And before we finish, we need to change the setup.py that I mentioned that we had to change eventually. And this is because we need to include here the extra files we have created. So for this, we need to import something. So we need to import the glob. And we need to add these two lines. So what are these? So again, we have the package name, and then we include the launch folder and all the files inside the launch folder that have _launch.py. And then we do the same for the config folder. So anything that has config, anything that ends with a .yaml file, okay, extension. And now, if we go back to the root of the workspace and we do colcan build symlink, should build okay. We need to source again, and now ROS to, instead of run, we do launch. And again, I need to redo eval for some reason. Launch Perceptron driver, and now if we do double tab, you will see here Perceptron launch.py, and this will essentially work the same, but as you can see here, still it could not open the serial port. Okay, that's fine. And as you can see, actually now it is trying to open the port TTY-S1, which is in fact the one that is on the config file and not in the code itself, right? So yeah. Yeah, I believe that's it for this driver. Now, again, now if you want to test this on your own robot, if you are using the Raspberry Pi, you will need to do this either by this USB to UART or find the solution so that we can communicate with Arduino and the Raspberry Pi using the TX RX pins. Sorry. If you manage to do this, I will now show you how we can, make our robot move. So that comes next. All right. So I have my robot here, and it is on right now. So the next step you want to do is to SSH into the Raspberry Pi or whatever board you have on your robot. To make this process easier, what I like to do is you go to the home folder and you go to .ssh. And now here you do a config, touch config if you don't have yet, like this. And then you open that file, config. And then you can create basically, yeah, like configurations for your SSH servers you might have. So in this case, you create a host with the name Perceptron. This is the name you will use to connect. Then this host as the host name, so the IP of your Raspberry Pi, for example. And then the user will be the username. If you are using the Raspberry Pi, as we did in the previous video, setting it up, this will be the user will be Pi only. Okay. So if you have that, we now do SSH Perceptron. Yes. My bad, it's not the same password. All right. So now I am inside my Odroid, and if I do ls, you will see that I have here Perceptron the workspace. So what you should do is, if you want to clone your own, then you need to clone. So git clone your own repo. What I do is I clone my repo. So Perceptron bot, not the workspace. You will see why. So you clone this. It should be here exactly. Clone this. And then so git, because I already have that. So let's do git clone. Now we'll change the name to test workspace, okay? Yes. All right. Yes. It's because this is using SSH keys, and I don't have any SSH keys yet on the board, which you should already have, by the way, if you follow the tutorial. So there we go, like this. So recurse modules essentially get all the Git repos I have mentioned on here. So this is another repo. In the low level, there's another repo, which is the motor controller, right? Either way, this will clone. This will take some time, because the Ethernet is not that fast with the Wi-Fi I have. But either way, if I go to this Perceptron workspace and oh, never mind. Actually, I did clone the Perceptron workspace. My bad. But I mean, you can do both. It's as you want. So if you clone the Perceptron workspace, the same procedure happens. So let me just check if I have ROS2. Yes, I do. So we go to the Perceptron workspace and we do source install setup.bash, right? As we did on the PC. Now we do ROS to launch Perceptron, and then Perceptron again, .launch file. And now this is now the driver working. And on your PC now, so sros eval ROS2 run teleop twist keyboard, and again. So this essentially is now a controller for control the robot. And if I press I, my robot should move, and it is not moving for some reason. Let's check here. So ROS to topic list, and that is because I don't see anything. So let's restart this. And let's check this again. Now we see this. Okay. So ROS topic list gives you a list of all the topics currently available. And before, there was nothing, right? Only the parameter events and the ROS out. I guess it's because I didn't have this sourced, the ROS, so I didn't know of this. So now that I rerun the driver node, now I have the TF, .dom, and command velocity. And essentially, if we try this again, the robot is moving. And now I can show you this. There. You can see the robot, they're moving. All right. And that's it. So now that we have this moving, I will show you something interesting. So let's create another terminal and let's do SROS again and Rviz2. So this is a visualization tool and we will see the robot moving in space now. So if you go here to add TF, search for TF, there we go. Change this map to ODOM. Remember that ODOM is the 0, 0 point, right? So I enabled here the names so that you can see. And so the robot is here, base link. And now if I move here the drone, you will see there it moving as well. There we go. So let me put this in a 2 view so it's easier. So I'm moving forward now, and as you can see, it's moving forward. I'm rotating. There we go. So the red arrow is the X, so that you know. And there we go. Now, something to take into account is that this odometry is not perfect at all. And the main reason it is not perfect as for the moment is that the wheels are spinning when we start moving. And that means that it still counts even when the wheel spins, but the robot is not really moving, right? So one solution we can have is to have this IMU, and with that we can see is the robot actually moving through accelerations, and then we can use some filters like a Kalman filter to basically fuse together odometry and IMU and then have a clean odometry, or at least our best. All right. So yeah, that's it for this episode, I believe. Again, I don't promise anything about the Raspberry Pi with the pins for the RX and TX. I was not able to fix this, so it could be that my Raspberry Pi's RX pin is fried. As I said, I have used 5 volts instead of 3.3, and so that's something you need to care about. Don't put 5 volts into your RX TX pins. If you want to use it, there are these devices that you can basically make a bridge between the Arduino and the Raspberry Pi that converts the signal from 5 volts to 3.3 volts. If I find it, I will leave it in the comments down below, or the description down below, sorry. So yeah, that's it. So if you have liked this video, make sure to like and subscribe if you want to see more. The next episode, I am not sure yet what I will do. Most likely it will be making the laser work, the LiDAR work, and then we can basically have our or use the navigation 2 stack to then make our robot autonomous. Okay, so I believe that next episode will be setting up the LiDAR. Okay, so that you have something in mind. When it will come out, I have no idea now. As I said on the previous video, I will be starting my exams period, and yeah, I have no idea when I will be back with that video. Nevertheless, yeah, see you on the next one.